All right. Welcome back, everybody. So today we are going to continue talking about disks and queuing theory, and then we're going to start talking about file systems. So if you recall from last time, we talked about device drivers, which are device-specific code that's actually in the kernel and provides a standard interface up toward the kernel and provides a whatever interface down to the hardware. So pretty much in a device driver, anything goes. It's all about providing the standardized interface up. And as I mentioned, for instance, in Unix, typically the way the standardized interface is broken is with something called ioctl, and there's a bunch of these ioctls that for each type of device, and those are how you do special configurations. The thing that I didn't say, by the way, about device drivers is that the device drivers are the biggest source of crashes in modern operating systems. So probably upward, depending on what statistics you get, upwards of 75 to 85% of all crashes, blue screens, et cetera, are device driver related. So this is a pretty sad state of affairs, yeah.
Why does that bring down the whole operating system?
Well, the reason it typically brings down the whole operating system is because the device driver is usually running at kernel level in the kernel, and so one errant write can overwrite who knows what in the middle of the kernel. So
is that like a huge argument for the microkernel?
So this is a pretty big argument for microkernels, except for the fact that unfortunately, oftentimes device drivers need to have kernel permissions in order to even get at the hardware. So basically, running a device driver at user level is still not able to be done very well, and it's a little bit of a research topic, but you'd like to run the device driver at user level if you could. And I mentioned, by the way, that device drivers typically have a top and a bottom half. Amusingly, what is top and what is bottom actually varies depending on who you talk to, but we'll go with this convention, which is a pretty standard one. The top half is the part that actually interfaces upward with the kernel. The bottom half is the part that handles interrupts. Okay? Any questions on that? Okay. Then we actually talked about disks and the fact that the reading and writing of data on disks is kind of a three-stage process physically. So you have to actually seek by bringing the heads in to the right cylinder. Then you have to do, then there's a rotational latency, which is you have to wait for the disk to rotate till you're sort of over the sector that you want. And then finally, there's an actual raw transfer time, which is the time for the sector to rotate under the head and get the data off. Okay, were there any questions on that? Okay. Now, the thing to note, which we're going to spend a lot of time thinking about, is the seek time is large, okay, relative to the other things. And so you want to really minimize seeks as much as possible. And that's why file systems typically do their best to put things that are related to each other on close tracks so that there's very little seeking. Okay. And then finally, if we want to have a complete model of the disk, we typically add another couple of terms in there. So here's seek time, rotation time, transfer time. The other terms we add are controller time. That's the hardware controller that we mentioned. You can come on down if you want. And then the queuing time is the part that I'm actually going to spend a little time on today, right at the beginning here, and that's trying to model the software. Now, as you can imagine, modeling the software is not an easy task because it's very complicated. And so we're going to use a simple model of a queue that will get us some information, but obviously it won't get us all the possible information. Okay? So if you take the time queuing, which is the time that the thing sits waiting in software, the time going through the controller, and then the three pieces of the media time, you kind of get the disk latency. All right? And obviously the highest bandwidth out of the disk is to never move the head at all and just grab a whole track as you rotate the disk around, or a whole cylinder, in fact. So are there any questions so far? Okay. Good. So today I want to continue on the queuing piece that we sort of started, and then we'll talk about file systems. So How many, just out of curiosity, how many people have ever encountered queuing theory before here? Anybody? Okay, 1, 2, 3. What class is that from? Huh? 250. Okay. So, good. That's a good class. So we're going to take a fairly simple model of queuing theory, and it looks as follows. We've got a queue in front of the rest of the system, which is the controller and the disk. And this queue is literally going to be a queue. So it will be FIFO. We'll put things on one end. They'll eventually work their way to the front. They'll get processed, and then we'll get a result out. Okay? And in some sense, we're going to treat this as a complete queuing system. So that's why I put this blue box around it. So we'll have arrivals for requests that come in. They'll sit in the queue for a while. They'll get processed. And then we have departures. Okay? And if you remember, how many people remember detailed balance from chemistry in high school? Remember that? Right? So I hate to bring that back up. But so basically what we know is that over the long term, the number of arrivals coming in better equal the number of departures. Why? Yes?
Otherwise, you're either summoning things out of thin air or things are accumulating.
Yeah, too many arrivals come in, the queue blows up, you got a mess, right? So basically we are, now in reality, there are bursts of time where arrivals are not equal to departures. And so queuing theory is specifically targeted, at least the type we're going to talk about today, at the steady state, not transients. Because once you actually start dealing with transients in queuing theory, it gets much messier very rapidly. Okay, so for the bulk of this class for queuing theory, we're going to assume that there's a steady state of arrivals and departures. Okay, and we'll go with that. And the first thing I want to tell you about is something called Little's Law, which is a very simple law that applies to all sorts of stochastic systems, whether they're kind of steady state or not. And it basically says that the mean number of tasks in the system is equal to the arrival rate times the mean response time. Now, this is McDonald's law, really. Okay? And what that means is you go to McDonald's at lunchtime and you walk through the door and there's a line. Okay? And there's a certain rate of people coming through the door. And you wait for a while, you get to the counter, you get your hamburger and fries and all that other healthy stuff that you get, and you leave. But just before you leave, you turn around and you look, and in the steady state, the line behind you is going to be equal to the line that was there when you came in the door. Okay? That's our assumption. And so if you think about this, that makes perfect sense. The mean response time is the time I waited in line. The arrival rate is how many people per unit time come in. If I multiply those together, it means that when I came in, there's so many people in front of me, and as I go through the line, when I turn around and look, there ought to be the same number of people behind me. Okay, and therefore, how many people behind it was the time I waited times the rate at which they come in. Okay, so that's actually not too magic here. Is everybody with me? So I basically take the rate at which they're coming through the door times the amount of time I waited in line, and that ought to equal the number of people in line. Okay. Now, this applies to any system in equilibrium as long as nothing is creating or destroying tasks in here. And typical queuing theory, as I mentioned, doesn't deal with transient states. And when I say typical, I really mean basic queuing theory, because there are whole books on transient queuing theory, but it's very messy. So now, I'm also going to very quickly breeze through something which I'm sure everybody remembers. Okay, so first of all, the server spends some time with customers. So this is the person making the hamburgers for you. And there's actually a distribution of times to make a hamburger. Okay, so there's some mean, kind of like 69.9 on the exam, right? And then there's some standard deviation, okay, which is basically the square root of the variance. Okay, so variance is sum of probability of a given test score times t squared minus the mean. Okay, or you can write it like this too. It's basically the probability of how far you are from the mean squared. Okay, and then the square root of that. Okay, so everybody remember variance and standard deviation? Okay, now, so roughly speaking, the mean is kind of where the center of mass of the probability is, and this is the most common time to hamburger. And the standard deviation is kind of how far away you might expect your variation in hamburger acquisition to occur. Okay? And obviously, when we're talking about disks, we're really talking about the mean time to service a request and the standard deviation to getting the request. Now, what's going to be interesting is the type of queuing theory I'm going to just show you today is interesting in that the shape of this curve does not matter at all. Only kind of the mean and second moments here matter. Okay? And so it's going to be, no matter what the shape is, if it has the same mean and same standard deviation, you'll get the same result out, which is kind of interesting for this particular model I'm going to give you. Not in general true. And so because of that, there's this other constant called C, squared coefficient of variance, which is just the variance squared over the mean squared. And dimensionless, so there are no units here. And different C's actually represent kind of different properties of the system. Okay, so obviously if C is 0, what do we've got? No standard deviation, which means what? Everything takes exactly the mean to occur. That's a deterministic hamburger maker. Right? So if C is 0, it means you go in and you get your hamburger in exactly 60 seconds always. Okay? If C is infinite or large, what do we know? Yeah, largely random, actually possibly worse because you could be there all day to get one hamburger. Okay, that's probably more like McDonald's. What about C equal 1? Okay, so deterministic is C equals 0. C equal 1 is an interesting one, okay, because among the various shapes that cause C to be 1 is this one which is exponential in shape, and this is the so-called memoryless distribution. And what's interesting about a memoryless distribution is that it doesn't matter how long you've waited for an event to occur. If you sort of say, well, I've waited this long, whatever it is, I'll rescale my probability distribution, and I'll say, okay, given that I've waited a minute, how long will it take? It turns out there's no information given you by how long you've waited. Okay, now this is the Berkeley bus, right? It doesn't matter, I've been waiting here for an hour, obviously the bus is coming soon. Well, no. The fact that you've waited for an hour has absolutely no bearing on whether a bus is coming anytime soon. Okay? So this is actually the probabilistic way of looking at a Berkeley bus. Okay? Now, what's interesting about memoryless distributions and why we talk about them a lot is that they kind of occur naturally in aggregates. So if you have, suppose you've got a lot of things that are all occurring at a high rate, and each of them has a weird distribution, but you put them all together and you kind of say, well, when is the next one going to occur? That kind of system, many things together, tends to look memoryless. Okay, and so if you don't know anything else, oftentimes people will call a distribution memoryless, because then the only thing you really need to know in that situation is sort of what the mean is. You know, it's sort of like, well, I don't know anything else other than the average, so I'll call this thing memoryless. And sometimes that's justified because it really is an aggregate that's somehow converging, and sometimes it isn't justified, but you should know that's an assumption that's made many times. Okay, question, yes? They have to be uncorrelated with each other. Yeah, well, the intuition is just that the fact that they're uncorrelated, the fact that you've waited so long for something to occur really doesn't say anything about when the next thing's going to occur. Because they're coming in randomly, literally. The other, just maybe this will help a little. If you take a memoryless distribution and you look at the actual arrival rate, okay, and what we do is we zoom in by shrinking time down to a very tiny little piece of time, and we say, what's the probability that something will occur in a given slice of time? It's actually a constant. The probability that you occur in an infinitesimal slice is constant in a memoryless distribution. All right, so you can imagine that if you have enough things all together, then there is a rate that's really constant. And so the shape doesn't matter anymore. It's more about the arrivals. I don't know if that helps you any, but that's another way to look at memoryless. Okay? So if we have a bunch of things together and we can compute what the average is, then maybe we could call it memoryless. And it turns out that the queuing models that we're going to do in class, because this is not a class on queuing theory, one of the input parameters is going to be memoryless, and it's going to be the arrival rate, okay, because that's the easy one to do. And so just so you know. Now, another thing that's interesting is disk response time tends to be more like a C equal 1.5 distribution, which basically means that the tail is kind of a little longer, and so there's some times when you have to seek when you didn't otherwise, and it tends to smear things out a little. Okay? All right, questions on C? So C is a unitless parameter, but C equal 1 is an interesting case. C equals 0 is an interesting case, and knowing that the disk may be 1.5 is something interesting. So the next thing that I want to give you before I, derive the queuing theory model that we're going to use is we got to talk about what's called the mean residual response time. And this is actually much simpler than it looks. So here it is. Ready? You walk into McDonald's. You look at the person at the counter, because they've already gone up there and asked for their hamburger, and you ask, on average, how much longer do they have to wait? Okay, so my experiment is I parachute into McDonald's. Dun, 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 dun. I look at the guy at the counter. How much longer on average do they have left? That's the mean residual response time. Okay, now let me make it very simple for you. Suppose that the hamburgers are deterministic, and they always take a minute to give you a hamburger. All right? Always takes them exactly a minute. And suppose that there's a line that goes out the door, so the person's always busy. What's the mean residual response time? Anybody? It's not a minute, because remember, you're dropping in randomly, so what's the average time left of the person at the counter? Yeah, 30 seconds, right? Because on average, if you did this experiment over and over again, there's 30 seconds left on average of the person at the counter. Okay, because you're dropping in the middle of you're randomly dropping in the middle. Okay? So this is the last kind of crazy thing we got to derive, and we're not going to derive it because it's complicated. I'd be happy to show you this on the board or something. But basically, the mean residual response time is actually 1/2 the mean, surprise, remember we just said that, right, 1/2 of a minute, times 1 plus C. All right, and this is derivable. You won't be able to derive this in your head, so don't worry about it. You have to take this on faith. But notice, for a deterministic case with C equals 0, it's 1/2 mean, which is exactly 1/2 of a minute, 30 seconds. Okay? Good. All right. C equal 1, this is interesting, right? What's the mean residual response time to somebody waiting at a bus for a Berkeley bus when it's a memoryless distribution? It's exactly the mean before, right? If the average bus arrival time is, once an hour, you pop in at any random time, and it's always going to be an hour on average till the next bus, no matter what time it is. Okay? Question, yes? You know what it is? Z is, so this is a notation where Z is kind of in a transform space, the Z transform space. So yes, it is a function kind of Z, but think of this as a symbol rather than a function. Okay. All right. Questions on this? Because basically now what we're going to do with this is pretty simple. So the hard part's done. We're going to use some algebra, which I hope is simple. You guys all remember that, right? Okay, so let's figure out what we want to know is if I'm going to arrive at McDonald's, what's the average time I wait for a hamburger? Does that sound like a good thing to derive? So what we have here is we have an arrival rate, which is the rate of people coming in the door, and that's defined by lambda, which is the number of people per second. And then we'll have a service rate. And remember, the arrival rate is memoryless. Okay, so basically the only parameter we need is the average rate. Okay, the service, on the other hand, will have any distribution that we're interested in. And so basically here, the average service time is how long on average it takes. And so we're going to talk about the service rate mu as 1 over the average time. So for instance, if the average time's a minute, the service rate is 1 per minute. Okay. So mean number of arriving customers per second. T is the mean time to service a customer. That was our M1 from earlier. C is the squared coefficient for the server. Okay, so the person behind the counter at McDonald's has a C. All right, if their C equals 1, they're memoryless, and therefore you end up with a chicken sandwich instead of a hamburger. That was funny, right? Okay, so now here's some derived parameters, right? So there are only three things here. So mu, the service rate, is actually derived from the service time. Okay, that's 1 over service time. The server utilization, which is the most interesting number that's derived here, is actually lambda over mu, or lambda times T ser. So what's utilization? Utilization is a number that when it's 1, the server is working as fast as they possibly can. They're 100% utilized. Okay, that means that there's always somebody at the counter all the time. What is that equal to? It means it's the rate of people coming in times how long it takes them to serve, or it's the rate of people coming in times the rate of over the rate of people going out. What about this number? Somebody explain to me why u is from 0 to 1. Somebody explain the 0 part. Yes?
You have no one coming in.
Yeah, so the 0 part of utilization is it's 4:30 and nobody's at the counter, okay? So you're idle. That's because lambda is 0, and it doesn't matter how fast you can make hamburgers. Somebody tell me about why is 1 the upper bound here? Yes? That's right. You can only be working all the time. So notice that u equal 1 is that critical piece that I told you guys about, which is the 100% utilized server. Okay, so u equal 1 is that point which we never want to actually hit. Is everybody with me? Again, it's the rate in over the rate out. If the rate in equals the rate out, it means that we're just barely making it. Okay? Any questions on u? Okay, and don't get u and mu confused. There's a little tail on the mu, right? So, okay, so what do we want to compute out of all of this? So notice so far I've got 3 red parameters which define my system: lambda, T service time, and C, and 2 derived ones. And now, suppose I want to talk about the time spent in the queue. That seems like a good number. Okay? Or suppose I want to know the length of the queue. Well, fortunately, because of Little's law, the length is easy. It's lambda times the time in the queue, remember? The length of the queue is the rate of people coming in times the time you spend in the queue. Yes, question? No, that's okay. Yes, so T service is independent of the arrival rate because T service is about the server. Oh, no. No, when you're at 100% utilization, the server is always busy. They're 100% busy. No, it doesn't actually. So we'll assume that this person, when they get 100% busy, doesn't freak out or flake out. And they just keep going at their same average service time. Well, no, hold on a sec. You'll see why it's not good in just a moment. Okay? It's going to be not good, but it's not going to be not good because the server freaks out. It's going to be not good because the clients freak out, and you'll see why in a second. Okay? So, did I answer that question? So, by the way, T-ser, notice I called this M1 earlier. So just so you know, what we're saying here is that the server has a distribution on making hamburgers, and they have a mean and a standard deviation, and therefore they also have a mean and a C. Okay? All right. What else? So how are we going to do this? How do we compute this? Well, I've given you actually all the pieces, and I'm not going to make you derive this, but clearly the customers in front of us in line have to get their hamburgers before we do. Otherwise, you got a riot, right? So that says basically the number of customers, which is the length of the queue, times the average service time, is the average amount of time to serve everybody that's in front of us in line. Okay, but that doesn't include the person at the counter. Okay, so to include the person at the counter, we actually have to say what is their residual time at the counter at the point that I walk in the door. That's mz. And what we do is we actually multiply the utilization times mz. Why is that? No, it's because if they're not 100% utilized, then basically I come in, there's some chance they're not utilized at all, and so this MZ is only about them being 100% utilized. So we scale it by how busy they are. Okay, so this is just M1Z is assuming somebody was definitely there. We scale by U because there isn't always somebody there. Okay, and then we just put these together. So the time in the queue is everybody in front of me in line, LQ times T sir, plus U times residual time, and poof, we're done. Now, I'm going to pause here before we do algebra. Okay? Ask a question. Does that make sense to everybody? So the time that I wait is equal to the time to finish everybody in front of me plus the time for the person that's actually at the counter at the moment I get there, the time they have left. Now all we have to do is just rearrange things a little. So ask your question, if you got it. Yes? Sure. So so M1Z was if the person's 100% busy and we drop in with a parachute and we say for the person that's there, which we know there is a person there because the server is 100% busy, how much time do they have left on average? Now, when the utilization is not 100%, but it may be less, then when we drop in, right, half of the time, let's suppose it's 50%. Half of the time we drop in, there's nobody there, and so the time is 0. The other half of the time, it's M1 of Z. And so when we average all that, the average time of the person at the counter when I take utilization into account is U times M1Z.
How did you ever have nobody at the counter?
Because this is an average calculation. So sometimes there are people in line and sometimes there aren't. Okay, and so basically this is taking into account the average behavior. Okay, now to do this 100% correct, there are different ways of deriving this, but you'll have to go with this one. Yeah, go ahead. Well, we want to actually try to compute what the average time really is rather than a maximum amount of time. Yes, question. No, we've made no assumptions on C here. In fact, as you notice, C is actually in this equation. You just haven't seen it. It's in M1 of Z. Wait, actually, did I have it right here? Oh, it's right here. See, C is inside of M1 of Z. So if you see M1 of Z is equal to that. Okay, good. Now, let's just rearrange here, okay? So here's our equation from the previous case. We do Little's law, which says that what? It says the length of the queue is lambda times TQ, so that's my substitution. And now we used utilization is basically lambda times T sir, so lambda times T sir is U. Okay, so now we got utilization times TQ plus utilization times M1Z. Okay, and now what do we do to get TQ? Yes? Well, or rearrange and divide by 1 minus U, right? So we rearrange like this and divide it out, and we end up with TQ is equal M1 of Z times U over 1 minus U. Okay? Just algebra. Ignore the man behind the counter. So what's interesting about this equation? What happens is U goes to 1. What happens is U goes to 1 to TQ. Okay, the line gets infinitely long, or the time in the queue gets infinitely long. Okay? All right, so here it is. I just substituted M1 of Z in here. So what's interesting about this is that as the server gets 100% busy, the queue or the time in the queue get infinitely long. And so that's why we don't want to go to a utilization of 1. Okay, now many of you are like, wait a minute, how did that happen? It's like, well, I divided by 1 minus U. But how did this really happen? I mean, what's causing this effect? You know, it's funny about it. It's not really the bandwidth being too high. It's something else. It's a good guess, though. What it is it's the randomness in the arrival rate. Because remember, a memoryless distribution I showed you has this tail? So when you're exactly equal to the rate in equals the rate that the person can handle, that randomness, those occasional tails keep building up. Because when there's a burst comes in, basically it doesn't get handled. Okay, I shouldn't say the tail. I should say actually the one over the tail. So it's the piece in the closed piece. Suddenly you get these bursts of a bunch of people that arrive, and the server never catches up. And those bursts occur occasionally. And even though the average rate in is equal to average rate out, the queue keeps growing. Okay, so the fact that there's randomness in the input means that this thing has the behavior we're seeing. Yes?
Don't you also have the randomness of maybe less than the average come in to get a little bit ahead?
Yep, you do have the less than the average comes in, but it turns out that with a memoryless distribution, and actually with most random distributions, the tails, unfortunately, you don't catch up on. There was another question in the back. Okay. So basically, so notice that as u goes to 1, tq's goes to infinity, and so our assumption so far, the system's completely in equilibrium. There's no limit to the queue size, okay? So we are sort of somehow assuming we've got an infinitely big McDonald's because we're allowing the queue to get infinitely long. Now, in reality, what happens is you come in to the parking lot and you see a line that goes out the door and wraps around 2 or 3 times, and you go to Burger King, right? Or in reality, in a system, there are blocking effects, right? Your queue can only be so big, and you stop being able to submit requests. So what happens when the queue is full is rest of the system blocks. Okay? But it is a bad scenario if your queue is not absorbing the requests, because you want the queue there to prevent people from getting blocked up. Okay? Now, we actually have 2 different types of queue here now that we could talk about. One is the general queue, which is what we call a memoryless input, general output, one server queue. Just hold on a sec. Which is this equation that I gave you before. And why do I say it's general output? Because I'm allowing C to be non-memoryless, something other than 1. Okay? An MM1 queue is memoryless in, memoryless out, and that's what I get when I set C equal to 1. And this is the much simpler equation if I have a memoryless input and a memoryless output, and it's just the service time times U over 1 minus U. Question? Yes?
Isn't the phenomenon we were just discussing almost also a consequence of the assumption you made that the arrival rate is always the departure rate? Because in order to guarantee the arrival rate is equal to the departure rate for those bursts, we have to have an infinitely long queue.
Yeah,
Those random, those outliers.
I suppose it's true. Yeah, I guess I suppose you could look at it that way. Questions? Are there questions? So now, okay, so we derived some stuff. It's messy. But what do we really do with this? Well, if you want to use it, all we're saying is for a given system, you need to figure out what lambda for the input is and C and T service for the output, and then you can kind of get an idea how big the queue is. Okay, that's all. And you do that by plugging it into these equations. And if it turns out that you have a totally memoryless server, then this is an even simpler equation. Okay? So let's, before we do administrivia, let's give a simple example. So here's a case where we have a disk where the user requests 10 8K blocks per second. Both the request in and the service out are exponential, so we're going to set C equal to 1. And the average service time is 20 milliseconds, which is going to be some combination of controller, seek, rotation, and transfer time. Okay, and so now we can ask some questions like, how utilized is the disk? Well, utilization, U, is equal lambda times T service time. So we could compute that. We will in a second. What's the average time spent in the queue? Well, that's what we call TQ. What's the average number of requests in the queue? Well, that's lambda times TQ, using Little's law. What is the average response time of the whole system? Now notice that this is different. This is the time from when I go into the door at McDonald's till I walk out with my hamburger, not the time I spend in line. So we've been computing the time in line. The time it takes me to get my hamburger is one more service time. So it's actually the time in line plus the service time. Okay? So how do we compute this? Well, lambda, how many customers per second? It's 10 per second. Okay, that's easy, right? 10 per second. What's the service time? Well, it takes 20 milliseconds to serve something, so that's 20 milliseconds. Now, by the way, make sure your units are the same. So 20 milliseconds is really 0.02 seconds. Okay? Don't mix milliseconds and seconds, or you're going to get a bad answer. Okay, what's the server utilization? Lambda times T ser. So that's 10 per second times 0.02 seconds is 0.2. Which is good because utilization is a unitless number, so there shouldn't be any units in it. Okay? What's the time in the queue? Well, we just compute. It's 20 times 0.2 over 1 minus 0.2. That's just T ser times U over 1 minus U. Gives us 5 milliseconds. Okay, so what's the average length of the queue? That's lambda times TQ, so that's 10 per second times 0.005 seconds, which is what 5 milliseconds is. 0.05 average things in the queue. So as you can see, we don't need much of a queue here. Okay, we need one slot. Now, we probably want more than one if there are bursts that we're trying to handle, right? But on average, we only need kind of less than one slot. We need 0.05 of a slot. And then finally, the total time to get serviced is TQ plus T ser, which is in this case 25 milliseconds instead of 20. So in this simple case I just gave you, it turns out when we account for the queue, we add another extra 5 milliseconds to our time. Okay, it would normally, if there's nobody in the system, it'd take us 20 milliseconds on average to get our disk request. Here we had an extra 5. What I encourage the reader to look at is imagine that you come up with a utilization that's higher. The moment this thing starts going above 0.5 or so, or 0.7, you'll find that this time creeps up very rapidly, and it'll be very soon far more time spent in the queue than spent at the disk. Okay, and that's because it's very nonlinear. Okay, that's my example of the queuing theory. We're going to stop there if we have any questions. Yeah, go ahead.
So, is this independent of the size of this request, or is that kind of morphed into the service?
That's a great question. Is this independent of the size of the disk request? No, I've morphed that into the service time. So this service time was crafted for an 8 kilobyte request. That's a good question. Okay. Any other questions? Now in section, yeah, go ahead. Well, notice that even though there's only on average 0.05 in the queue, we end up increasing the service time by 25%. So it doesn't take a lot of things in the queue to increase time on average. And if you're asking me how many are normally in the queue, it varies on what your utilization is. You'll find that as your utilization goes up, you get around 0.7, it gets very large quickly. Okay. Good. All right, you are now enlightened about one use of queuing theory. Now, what are the limitations of this? Steady state, average behavior. Okay? How could I possibly talk about steady state memoryless input to a disk system? Can somebody justify why this is not a bunch of pointless computation? Why might this even be meaningful? Yeah. So at very least, it educates a lot about what we don't want the system to do. I'll buy that. Could this be thought to actually apply to an operating system with requests to a disk? Obviously, I'm trying to. So what argument might I use to try to mean that this makes sense? And I'm agreeing with you, by the way. But what else? Anybody? Yeah, go ahead. Take a stab.
I was going to say something about basically like if your physical memory is full, since processes usually have locality, you can kind of say that this kind of models the like demand paging request.
It might. I guess what I'm going after more is why could I say that a memoryless input means something? Okay, I'll put you out of your misery. So the idea here is if there are a lot of processes making requests and they're independent of each other and uncorrelated, then we might be able to compute the average request across the set of them, and that might be a justification. Okay? It's a stretch. But it is a way of getting an order of magnitude idea about how bad your system is. Yeah, question?
Can you just say that after a system's been running for a while, it won't trend, or like this access pattern won't trend one way or the other?
Yeah, I don't know that you can say they won't trend because your system probably goes in phases. I mean, a very clear phase is you're booting it and there's a zillion things happening that don't happen again, right? So that's at least one phase or two phases. And typically there are a lot of other ones as you start new apps and stop apps and so on. So I don't think I would say it will never trend anywhere. Yeah. If there's a dominant process in the system, maybe this falls apart unless it generates requests in a way that's somewhat memoryless and random. I mean, it's sort of, you could still try to apply this even if you had an average set of requests that weren't memoryless. It will mean less. But again, go ahead. Right. Yeah, so again, there are people that will tell you that queuing theory is the world's solution to modeling things. They're stretching it, okay? However, it is a good way to get some idea what domain your system's in. That's what I want you to go away from with this. I don't want you to think that the queue is going to be exactly 0.05 items on average, okay? But it will tell you something about the system which is a lot more than you had before. Yeah, question? Uh-huh. Yeah, I think it's going to depend on what your requests are, whether it's maximum or not. And if you're really curious, by the way, there is a GG1 queue. So there is a queuing model for general input other than just memoryless. It's just a lot messier. And I would not subject you guys to it. But, okay, good. Whew. Now, what are some resources? It turns out that the handouts page actually has some photocopied pages from Patterson's book on queuing. He's actually got a graduate computer architecture book, and there's a chapter on queuing theory, which you can take a look at, which basically rederives what I did. And I also have a link on there with a complete website of queuing resources if you want to know. And queuing theory is actually quite interesting, and it's done a lot of made a lot of interesting discoveries over the years having to do with networking and telephony and a whole bunch of things. So there's a lot of utility to it. So if you have any interest, I would encourage you to take a look. If you want to look, there's actually midterms with queuing theory questions. A few midterm 2s from previous years have them. Assume that queuing theory is certainly fair game for the final, okay, and or possibly midterm 2. Now, speaking of which, so two things I want to mention. So one thing is Friday is going to have a feedback section. We'll have a feedback form that you can fill out that says something about how the course is going and how your TAs are doing and so on. Please go to section to fill that out. The other thing to go to section is, last time when I had people raise their hands on midterm 2, I didn't actually count. It looked roughly equal. And then some people were like, it wasn't really a fair count. And it's like, oh, okay. And then also, the other thing about midterm 2 is I realized that suddenly springing a just day after Thanksgiving thing on people may or may not be really fair. Okay, so, however, Friday we'll have the official vote. Okay, you come, there are no proxy votes. Okay, can't vote for your friends. You can't vote for friends that were in the class last year. Come, tell your TAs will get 2 numbers per class. And if you're not there, you can't vote, but everybody goes to section all the time anyway, so that's not a problem. Okay? If it turns out that we don't have a midterm for some reason, what I'll tell the people that feel that they really want a midterm is the one we just had was only worth 20%. Okay? The projects are 50. The participation is 5, so there's a lot of other options there. The final there's a lot of chance to do well in the final. So I don't know how this is going to turn out, but I figured we should make it a fair vote. Okay. All right, is everybody okay with having a fair vote? Because I can either put the test in or not, because we've got the room, and we've got the infinite time of the faculty member and TAs to produce the test and grade it. So, all right. I'm kidding, by the way. Okay. Don't forget group evaluations, very, very, very important. And make sure you participate in your groups, because if you don't participate, it's potentially a zero-sum game. And if you're having trouble with your groups, or your group is having trouble with you, or some combination of the two, make sure to come talk to TAs or myself. Let's try to resolve it. We've got 2 projects still, so there's still hope. Okay? Hope for everybody to get along, kind of like Obama said today. So it's an interesting speech. I don't know if any of you have any regrade requests, but remember they have to be submitted written to your TAs. So make sure to do that. And that's also true if you want to have regrade requests on your projects or something. Okay, make sure to write up the request. Okay? Any other questions on Administrivia? Yeah.
Are there going to be any sample finals?
There are no sample finals, but you could imagine if for some reason we didn't have midterm 2, that the questions on former midterm 2s might indicate something about the final. And the final is basically the whole class from a material standpoint, and therefore questions from all the midterm 1s are game 2, but I mean it's things to look at. Now if it turns out we don't have a midterm 2, there will be a focus on the second half of the class, but there'll still be potentially questions from the first half. So, okay. Good. Okay. So make sure, by the way, to always check glookup on all your grades, because if we got them wrong and you don't tell us, then we get them wrong. Unless, of course, you got a grade that's over 100%, then we might notice that. But okay. So before we take a break, let's finish up something about disk scheduling. So what I wanted to say on another topic here is a disk can pretty much only do 1 request at a time. So how do you decide which request to do and in what order? So suppose we've got this request stream coming in. Track 2, sector 3, track 2, sector 1, track 3, sector 10, et cetera, et cetera, et cetera. What's the right way to send those requests to the disk? Yes, go ahead.
You want to maximize the cylinder, so you want to order them such that they're all the same cylinder conditions.
So we'd like to avoid head movement, okay? Right, because otherwise that's, be expensive. So one option would obviously be FIFO order, which is not what you just said. And the thing that's nice about FIFO order is, I guess in some strange sense, it's fair amongst the requesters. So if each one of these requests is from a different process, what we know is every process gets sort of the same access to the disk. The problem with this theory is, as was just pointed out, you're not really using the disk well, because you may be forcing a lot of head seeks, a lot of movement when it's not required, and sort of everybody loses. Even though it's fair, they all lose. Okay, so it's not clear that fair and loss is a good thing. So a different option here is what I would call the shortest seek time first. And so the idea here is you look at where the head is and the rotation, potentially the disk, and you pick the request that's closest. All right, so you might go to 1, then 2, then 3, then 4. Okay, and although it's typically called SSTF, shortest seek time first, today you really have to include the rotation in the calculation, since rotation can be a significant part. So this sounds like a better solution than FIFO, right? Because we're moving the head as little as possible. The downside, as I mentioned here, unfortunately, is that it's great at reducing seeks, but it can lead to starvation. Because if you have one process that's busy doing a bunch of requests in one part of the disk and another process in another part of the disk, the first process may get all the requests and the other one may never get to go. Okay, so although this seems to optimize the head movement, it's not guaranteed to be very good overall, because we may starve out processes. So that leads the scan algorithm, or otherwise known as the elevator algorithm, all right, which you probably have even heard of before. But the idea is you take the closest request in the direction of travel. So imagine an elevator, right? It's going up. It will stop for everybody who wants to go up, but it won't stop for people going down, right? Until it gets to the top, and then it goes down. Okay, so that's why this is called the elevator algorithm. So the idea is we're scanning in one direction in and one direction out to catch all of the requests that are there, to basically do a combination of minimizing the head movement as much as possible, but also putting fairness in there. So eventually everybody gets taken. Okay? Yeah, question?
Could there be like one where, since like the outer ring is rotating fastest, where you try to prefer set up data that's like an outer ring, is that way you
Yeah, you could try to do something that maximizes the outer ring use, but the problem is that the moment you have something in the middle, then it might be unfair to the people in the middle, so you'd have to ask. Yeah?
Isn't there still a problem where the program is reading and writing from the same ring the whole entire time?
So if you actually have somebody that keeps submitting something from the same track all the time, fortunately, the software time to get the requests in is typically longer than a rotational time, and so you would never get into that live lock scenario. But yeah, that's an interesting thing to worry about. And if you were getting that for some reason, you could always sort of limit the total number in a given floor before you went up, for instance. Elevators do that by beeping when you got too many people in them, right? So there is a variant called C-scan, which your book talks about, circular scan, and the idea here is you're trying to avoid bias at the top and the bottom, where you get a little bias because you're kind of going one direction and you're going in and back out, but the edges sort of get preferential treatment in that, right? Because you're spending more time in the end of the beginning. And so what C-scan does is it always services requests in one direction, zooms the head in one direction. So it's always, it only goes up, okay, and then it magically teleports to the bottom floor and then goes up again, okay? And you could argue that this one is less biased and a little fairer than scan, but I don't actually know of anybody who implements it, because why waste your time down when you could be picking requests out, right? Okay. Questions? Good. All right. So, who does the elevator algorithm? Who implements it? Go ahead. What? File system. Who said file system? Okay, file system. You'd think. Who else? Yes.
The firmware on the hard drive.
Yeah. So it used to be in the old days the operating system did this. Okay, which is great because the operating system knows what's going on. The problem is that MS-DOS was a very dominant operating system for a long time, and MS-DOS was very unclever. And as a result, the disk manufacturers, in trying to give advantages to the MS-DOS users, started putting more and more intelligence into the firmware of their disk drives. So today, the disk drives themselves, the firmware on the controller or the disk drive, actually does the elevator algorithm for you. So the operating system submits a series of requests. The disk drive and or controller, depends on what type of system you've got, is busy reordering things independent of the operating system. Yes?
Does that mean the disk, modern disks, have like a little CPU or a little memory
Yeah, modern disks have a lot of intelligence in them. Question, yes?
Is there any disadvantage to that? It seems like the hardware can do it faster than OS can anyway.
The disadvantage is when the OS thinks that it's reordering one way and the disk is reordering another. And it might be if the operating system is specifically, can't talk today, trying to favor some part of the disk for, say, a database or something, then it doesn't really have control because something else is happening. And so you could say at the worst what's happening is the operating system's wasting time reordering things. Maybe that's the best case, is it's wasting time, excuse me. In the worst case, it's trying to do something specific policy-wise and it's being defeated by the disk. Yes?
It doesn't also the operating system have the advantage of knowing what might happen in the future as opposed to the firmware, which only knows what the request is given.
Yeah, I mean, you could imagine the operating system knowing a lot more than the firmware of the disk does. But unfortunately, it's not clear you can buy a non-smart disk today. So that option isn't there. Yes? There might be programmable, well, certainly any disk you buy, you can change the firmware by uploading it from the website, typically of the disk manufacturer. But whether they have disk programming kits or not, I'm pretty sure they don't. Because the timing on the firmware of the disk is extremely tight. And if you do something wrong with it, you're likely to lose data. And manufacturers don't like to be responsible for data loss. Yes?
So, do modern operating systems do they make any attempt to do disk scheduling, or do they just throw them all to the disk?
Amusingly enough, a lot of modern operating systems still have that code buried in it that's trying to do the scheduling. I think people have been pulling it out over time, but it's often still there. Yeah? Yes. So most disk drives, if you actually look at their statistics, there is some amount, for example, 32 gigabytes of RAM on disk. Okay, and you'll see that in the spec. So that's part of the buffering process. And we'll talk about seeking in a moment, but modern disks often typically have what are called track buffers, which allow you to buffer a whole track at a time. Okay? So, yes? This probably doesn't limit file systems that much. It does limit the amount of optimization that, say, databases used to do when they knew where every block was on the disk. We'll get to that part in a little bit. Okay, let's take a break. We'll come back in about 3 minutes or so and continue. Sorry, my time's a little late here. Yep. All right. So let's switch gears from the low level to the high now, and let's build a file system. So what's a file system? So it's kind of a layer of the operating system that takes the blocks from the disk and turns them into actual contiguous things, okay, which we often call files or directories or whatever. And some components of that are maybe disk management, which is turning blocks into files, naming, which is basically how to turn names into actual locations of items, protection, figuring out perhaps which blocks belong to which users, reliability, durability. So these are some of the ilities that we often talk about, which is how do you make sure that even if the disk sort of starts losing parts of your data that you're able to recover it. Okay, and what you may not realize, and I didn't talk a lot about, is that the storage of data on the disk has a lot of error correction codes on it because a lot of that individual bits get corrupted. And if you didn't have the error correction codes there, then you'd be losing data off of your disk every time you wrote it. Okay, so that's an important part. More interesting reliability, durability we'll talk about later in the term might involve, for instance, spreading data amongst different countries as a way of making sure that no earthquake or tsunami or whatever actually lost your data. So that you can go very far with the durability issue. So let's talk a bit about the user versus system view of a file. So the user's view, which is not the kernel writer, is here we have a durable data structure that we can use. So we write the data on the disk, and when we pull it back, it's there. Okay, but the operating system has a system called interface, which is really deals with a collection of bytes. Okay, so you implemented that interface last project. There's open, there's read, there's write. And if you remember, read and write were all about give me so many bytes. There's no reference to blocks in the system called interface level. And interestingly enough, the user may be thinking about data structures that are stored in the file, but the system call interface doesn't care what those bytes are. They're kind of an unformatted collection of bytes. Then finally, inside the operating system, it's really a collection of blocks. It's not a collection of bytes, okay, because the block is the logical transfer unit off the disk. Okay, and a block, by the way, is bigger or smaller than a sector, or the same. Which is it? Good, bigger. So sector is the minimum unit for the disk, but typically operating systems take multiple sectors to get a block size they care about. So that block size is usually associated with the virtual memory system, right? So it might be 4K or 8K, whereas the sector size could be 1K or something. It could be much smaller. All right. So how do we go from the user to the system view? So what if the user says, give me bytes 2 to 12? Yeah, question.
Yeah, what was the advantage of joining sectors to make blocks?
Say again?
What was the advantage of joining up multiple sectors to make a block?
So the advantage of joining out multiple sectors to make a block is that you're basically playing with the overhead to fetch, because you're saying, I'll never fetch just a sector, I'll always get a block, and therefore you get sort of more sequential locality off the disk. So you're always grabbing bigger chunks, so it's more efficient. And then oftentimes the size of the sector that was chosen on the disk had to do with an efficiency at the error correction coding level, whereas the block size is more about being efficient at the virtual memory level. And so those two don't always match exactly.
If you're trying to get locality in terms of the disk read, though, couldn't you just rapid fire request a bunch of sequential sectors? And the only overhead I see is you have to send multiple requests for multiple blocks. Presumably that's small compared to time. So.
Yeah, except that if you divide, think of it as the smaller chunks you take off the disk, the more information you need to keep about a file. Right? Because if you've got 4 sectors per block, you need to have 4 times as much information when you talk about what the file's got in it. So it's an efficiency from that standpoint too. Yeah.
What's the average size of a sector on a modern drive?
So it's, say, somewhere between 512 and 2K or something. Probably 1K is pretty average. Okay. They're making them bigger, by the way. I think I was actually reading about, the problem is that as the amount of information on the disk keeps getting denser and denser, they've actually started to go to really large sectors. This is a new thing. And so I think I was reading about 16K sectors, actually, on some new disks, which is, that's a phase change in size there. Yeah, go ahead.
So if you took one of those hard drives and you plugged it into one of these, will our OS automatically do that process?
Usually the file system depends on the particular operating system it was formatted for. And so if you were to go to something with a different block size, probably just a different operating system, clearly it's going to be not able to interpret that file system. Yeah, usually you have to reformat if things are completely different. So operating systems can deal with multiple different file systems. But if you're trying to use the same file system with a different block size, then that's not something that they're usually very easy to deal with. Okay. Not saying it can't be done, it's just not done too often. So how do we get from user to system view? So if the user says, give me bytes 2 to 12, the system has to actually figure out what block has those bytes, fetch it, and then return just the correct portion of the block. Right? The user would not be happy if they said, give me bytes 2 to 12, and the operating system came back with 4K or 8K, right? Because it would be kind of violating the semantics they thought they were getting at the system call interface. Now, if you're kind of wondering why we sort of implied that you should be blocking things up in your read and write system calls in the last project, the reason is that this is kind of like what really happens inside the operating system, because typically you load blocks off of the disk into the file system cache, which we'll talk about, or the buffer cache, and then you go from there to the user. Okay? Now, what if they say to write bytes 2 to 12? Well, notice that's actually more complicated, because you have to fetch the block, you modify the write portion of the block, and then you write out the block. Okay, why is that? Well, because we only wrote bytes 2 to 12, so there's a whole bunch of the block that didn't change. Okay? So you can see how mapping a byte interface to a block interface has a little bit of complexity to it. I'm not saying it's hugely complex, but you have to be careful. So everybody see that if I don't do this read, modify, write, I'll actually end up modifying a bunch of parts of the file I didn't intend? Yeah, there's no masking in a disk, typically. You've got to write a whole sector or read a whole sector. So that's a good question. Question? OK. So everything inside the file system's in the whole size block. So for instance, if you do getC and putC for a file, basically the internal buffers are going to be pulling blocks in. Okay, just because I asked for a byte. Well, too bad. I got to get 4K off the disk, and then I can give you your byte. It's just, that's the reality, okay? Now, that means that we've got to take some way of taking all the blocks in a file and structuring them in a way that keeps track of what order they're in the file, so that I can easily say, well, if I want byte 1 million out of this file, which block is it? Okay, well, the simple thing might say, well, you take 1 million and you take it divided by a 4K block size, and then you take it mod the 4K block size, and that tells you an offset in the block. Well, you could come up with an algorithm like that, except you'd be wrong, because it's not the case that a file is a contiguous map of blocks on the disk all the time. Okay, the disk is a random box of blocks, and we got to somehow turn it into a file. Okay, and so that's where the file system comes into play, because it needs to structure the blocks in a way that lets it get the file back. Okay? All right. So from now on, we're going to treat files as collections of blocks and go from there. So before we do that, let's talk about the basic entities that we're going to try to manage here on disk. We've got files, which are usable, visible blocks, groups of blocks, okay, arranged sequentially in some logical space. A directory is typically a user visible mapping from names to files. Okay, and oftentimes directories are actually stored in files, surprisingly. Okay, and we're going to access the disk as a linear array of sectors. Why is that? Well, because you start in the inner track and you work your way out, and you've got a sort of, the inner track's got a bunch of sectors, and then the next track is a bunch of sectors, and so on. And the question is, how do we address those sectors? And one option, which was popular for quite a long time, was you identify sectors as a vector of cylinder, surface, and sector. Which cylinder is it on? So that's where the head goes to. Which surface is it on? That's which of the heads do you use? And then which sector is how far do you rotate to get to the block? Okay, so this 3-tuple is enough to identify every block on every disk. All right? Now, obviously, this 3-tuple is unique per disk. Okay, if you have 2 disks, they're going to have 2 blocks that have the same name to them, obviously. Okay. Now, this was, again, the way things were done because it seemed simple to everybody. And what's great about this naming scheme is that the operating system wants to optimize by putting a file on the same cylinder to minimize head movement. It knows what cylinder. It can pick one, and then it can pick which surface and which sectors. And it can do anything it wants to optimize locality on the disk. So this seems like a great way of naming blocks, right? More power to the OS. Except then there was MS-DOS. And what about MS-DOS? Well, MS-DOS went along with the IBM PC, which had this thing called the BIOS, which we won't talk much about, but it is ROM that's sort of in every machine that has some standard functionality for reading and writing disks, blocks, and for booting and all that sort of stuff. There's some standard set of things that were originally developed in MS-DOS land. And what's amusing about the BIOS is it actually had a limit on how big the disks could be before it didn't work anymore. Okay, and this was because, the BIOS was developed in the days where the maximum memory size that anybody could ever need on a machine was 640K. Okay, and so there's a lot of other numbers that were just way too small. And so disks started getting big, and at some point, it was like, well, we can't name them this way anymore because the BIOS won't know what to do. So then what? Well, you go to something completely different, and you go to what's called logical block addressing, which is every sector has an integer address that starts at 0 and goes up from there, and the disk firmware manages this. So the mapping from block number to cylinder surface sector is done entirely inside the disk. The operating system, and the BIOS in particular, is not required to know anything about it. Okay, so almost any disk that you can buy today has a logical block address scheme now. Okay, now some things that are a little unfortunate about that is, for instance, you're completely hidden from what's on the same cylinder surface sector. You don't know that anymore. The best you can guess is that 2 block addresses that are close to each other on the disk. May not be entirely true. It's probably a pretty good guess. All right. The other thing is typically firmware on modern disks filter out bad blocks. So while in this old cylinder surface sector case, there might be some of these tuples that are actually bad blocks, and the operating system needs to know that, modern disks often hide that entirely from the operating system. Okay, so these disk drives are pretty smart entities. Okay, and it's up to the controller to basically translate from address to physical position. So in the first case, it's easy because, like I said, the OS deals with the bad sectors, and the only thing that's happening is the cylinder goes directly to a head movement and surface and sector, so on. Second case, the hardware completely shields the operating system. So, all right, any questions on that? Yes?
The hardware is shielding the OS from bad blocks. Then how does the OS know that the hard drive is having trouble? Does it have error bits, or what does it do?
So what happens in the formatting process is the bad blocks are written out of the logical block structure. So there isn't even a gap in the logical block structure. It just kind of skips over the bad blocks.
The logical block structure is defined during format by the OS.
Yes. No, by the drive during format. The drive figures out what blocks are bad, and it comes up with its logical block addressing based on that. Yeah, this is sort of the lower level format than the typical format you're thinking of. This is sort of the initial format before the operating system gets along to put a file system on it. Yes?
So it's like the logical block, what the operating system is allowed to use, what the disk gives to the operating system.
Yeah. The logical block address is the interface between the operating system and the hardware as far as blocks. Yes? So what happens during, no. So basically, once the blocks are assigned, you can't reassign them without reformatting everything, losing all your data. So at some point, blocks might go bad, and then the operating system has to remember which logical blocks are actually bad, in addition to the ones that the operating system or that the hardware has mapped out. Okay, go ahead.
So the drive only protects the operating system the first time it ever figures out its logical block.
Well, and it's giving it a level of indirection on block names. Yeah. Okay. So now, obviously, we need a way to track the free disk blocks. And so one option originally was you link free blocks together. That's a little too slow today. Another option is we could use a bitmap to represent free space on the disk, and people normally do that. And finally, we need some way of tracking the structure of the files. And this is typically called a file header, or we'll call this an inode next time. And the idea here is this tracks which blocks belong to which offsets within the logical file structure. So remember, suppose you got a file, it's got 3 blocks. What I want to do is I want to not only know which 3 blocks, but I want to know which one's the first one, the second one, and the third one in the file. Okay? So that's what the file header does. And now we can talk about a file system as defining what the file headers look like. And we can talk about a file system's optimizations as trying to make sure that the files, that the way the file header uses blocks tries to maximize sequentiality on the disk, so that most of the time when we read a file, we're reading sequential things off the disk. Okay, so that's going to be the goal of developing our file system policies. All right, is everybody with me on that? All right. So finally, when we're designing file systems, next lecture, we need to know something about how they're accessed to really help us a bit. And so we might ask this question, like, for instance, how do users access files? And their access patterns may define a lot about what our file system is going to look like. For instance, most files are accessed sequentially. You start at byte 0, and you read byte 1, then byte 2, byte 3. You read till the end, and you're done. Okay? So this says that any file system structure we come up with better do sequential access well. Okay, now today, you guys are used to sequential even more than anybody else ever was. Videos, right? Sequential. Music, sequential. Oh yeah, reading .c and .java files. Okay, that's sequential as well. But probably multimedia is the ultimate sequential. Now the other thing, of course, is random access is still useful. This is for databases and other types of files where you need to be able to go into the middle of the file and modify it, or go read something from the middle of the file. Or in the case of a cough file, for instance, which you're well familiar with now, you need to be able to pick out a particular block in the middle of a cough file, right? So this is less frequent, but still very important. And so we're going to judge file systems by how well, not only do they do sequential access, but do they do random access well. Okay, and then finally, there's kind of this interesting discussion that you kind of think about every now and then when you say, well, I could put a 2 terabyte drive into my phone. That won't happen for a little bit, but not too long. Then what? Well, now I've got 2 terabytes worth of information that's carrying around with me. How do I find anything? Well, you put it in a directory structure. Yeah, right. Okay, what's 2 terabytes worth of videos in a directory structure look like? Okay, it's a mess. So in fact, what we really probably want, but most file systems don't support this well, is some sort of content-based access. Find me 100 bytes starting with Kubi in my 2 terabytes of disk. Okay? Anybody here install Google Desktop on any of their machines or anything like that? Okay? You all know about Google, right? So Google is this. Google is this for the web, right? Type a word, shows you pages. The idea behind Google Desktop and this notion is that in the future, file systems are going to be such that you sort of type what you want to find and it finds it for you, rather than, gee, I got to put this in subdirectory A, subdirectory B, you know, whatever, which is unfortunately not very useful when you have a whole bunch of data. Okay, so we'll judge, so we probably won't do much content-based, but we'll certainly judge our file systems by sequential and random access. So in conclusion, so we talked about queuing theory today, which was a lot of fun, I can tell. We talked about two types of queues, the MM1 and the MG1 queues. This is the equation to remember. And the key thing here is that as the utilization goes to 100% or U goes to 1, latency goes to infinity, which is kind of unfortunate but true of pretty much any system you're likely to run into as an engineer. We talked about file systems which transform blocks into files and directories. We talked about optimizing for access and usage patterns, and we're going to maximize sequential access and allow random. And so next time we'll actually, and we talked about inodes, file headers. Next time we'll talk about several schemes, multi-level index, Demos, and also talk about naming. So that'll be next time. I hope you guys have a good weekend. Good luck on Project 3. Reports are due, or initial design doc on Friday, right, I think? See ya.